Hello, I'm Jane Adams from Northeastern University, and I'm presenting our empirical evaluation on augmented reality as a visualization technique for scholarly publications in astronomy. Astronomy is a highly spatial field. When astronomers need to visualize their data, the most true-to-life representations are often point clouds or volumetric meshes. But the current landscape of tools for astronomy journal publications lacks robust options for 3D representation. Astronomy paper authors are often stuck either showing small multiples of many viewpoints, hosting videos elsewhere, or needing readers to install special 3D viewing software and download 3D models. This was exactly the problem that Zucker et al. Experienced when trying to share their research. By looking at one part of the sky from lots of different angles, these astronomers saw that two regions which at first appeared to overlap when looking from Earth were actually two discrete blobs sitting tangent to a big bubble that could tell us about the age of the universe. Without a navigable 3D representation, we Earthlings might never have discovered this interesting story in outer space. But how could these researchers put their findings in the hands of their readers to give their readers the same aha moment that they had without needing the use of a computer and scientific computing software? A new option emerged as a potential solution: augmented reality in journal publications. By embedding a QR code directly in a publication, the authors provided readers with the means to pull up their 3D model in a situated visualization, that is, right on a mobile device beside their paper. They included two AR options in their paper, one as a typical AR rendering, stamped onto a table, another using a tangible device called a merge cube, which would allow readers to hold the supershell in the palm of their hand with a sort of 3D QR code object. The merge cube is a six-sided object with a unique pattern stamped on each face, which allows for easy tethering of 3D objects. Merge is used often in classrooms for K-12 education. Importantly, the astronomers were able to create these data visualizations using tools that were already familiar to them, such as GLUE. GLUE is a visualization software system for multidimensional linked data exploration, and it is very popular among astronomers for analyzing a combination of spatial and informational data. From GLUE, they exported directly to the MergeCube software. This meant that they didn't have to build their visualization in a new software. They were already using GLUE for their analysis, and now they could share those visualizations with readers without their readers having to also download the analysis software. This presented us with interesting questions from a data visualization standpoint. How well can users operate these new tools? Is one AR method better than another? Does augmented reality outperform a regular 3D rendering? And are there demographic differences in the difficulties of each method? So we decided to investigate. Here are the three experimental conditions we were evaluating: non-AR, just 3D on a phone; AR tabletop; and AR tangible. Luckily, we knew the perfect place to find prospective end users of these tools. The 2023 meeting of the American Astronomical Society taking place over 3 days. The AAS graciously allowed us space in the exhibit hall to perform user studies with 52 experts in the field of astronomy. This was a mixed method study, so we had two quantitative hypotheses alongside our qualitative observations. Our first hypothesis was that AR would be easier to use than non-AR. Our second hypothesis was that both AR methods would be the same amount of workload. We tested 6 tasks, including rotation, selection, comparison, and counting, on visualization types such as isosurfaces and 3D point clouds. Since astronomers can focus their research on very disparate parts of the sky, on many different scales, we chose the lowest common denominator of tasks by sourcing K-12 educational data visualizations to test user interactions. We collected information about participants' research area, demographics, familiarity with AR, and physical differences. Then we randomly presented participants with either one of the mobile AR technologies and a non-AR 3D rendering. While one of us directed the user in their task, another tester took careful observational notes. After solving the first 3 tasks on the first technology type, Users were presented with the NASA TLX questionnaire, which assesses the workload of a particular task encompassing stressors such as physical difficulty, mental load, and feeling rushed. After completing these Likert scale questionnaires, users were given the second technology. So if they'd started with augmented reality, either on a table or with a tangible, they were switched to the regular non-AR 3D on a phone condition, and vice versa. This allowed us to compare within subject the perceived workload between AR and non-AR conditions on mobile devices. For the second technology, users were observed while completing the other 3 tasks out of the 6 total, the tasks they hadn't already solved. Again, these tasks encompassed a variety of data types and interaction formats, mimicking the variety of parameters that authors publishing in astronomy journals would need in real life to communicate their research. Following the completion of these tasks, users were again presented with a NASA TLX workload questionnaire. Finally, we had an open-ended conversation with each expert astronomer about their experience. We asked questions such as, what did you think of this technology? How would you compare it to the other technology? Which did you like better? And did you see this as being useful for your work? Why or why not? At the end of the study, users were compensated with their own tangible device, the Merge Cube, to take home. Each study took about 25 minutes, though some users were very excited about the technologies and spent extra time exploring the data. We interviewed 52 experts in total. So, what did we find? Well, we had some quantitative hypotheses to test, our first hypothesis being that AR would require a lower workload than the non-AR technology. After all, we reasoned, having a celestial object floating on the table or holding it in your hand seemed like it would be more intuitive to use than dragging fingers across a phone screen. Well, it turns out that wasn't quite right. Women appeared to have an easier time using the non-AR technology, according to the NASA TLX workload questionnaire. In men, there were no significant differences between the AR and non-AR conditions. The average paired difference in TLX scores among men was also in favor of the non-AR condition, following the same pattern that was observed with women, but this effect wasn't statistically significant like it was for women. Why? Well, observationally, tasks in the non-AR condition appeared to be solved more quickly. People using the non-AR condition would often just quickly give the phone back to the tester after completing the tasks, whereas in the AR conditions, people often continued to explore the visualizations and make more observations outside of the task requirements. Sometimes we even had to remind people that they were in the middle of a study and that they needed to return our testing device. Our second hypothesis was that tabletop AR and tangible AR would score equally on the workload questionnaire. Remember that no participant used both technologies, so this scoring was between subjects. In line with our hypothesis, there were no significant differences between AR technologies. The average workload score for the tabletop AR condition was higher than the tangible AR condition, but this result was not statistically significant. Okay, so let's recap the quantitative results. Non-AR was easier than either AR technology for women, and non-AR was about equal workload as both AR technologies for men. In comparing tangible AR to tabletop AR, there really wasn't a notable difference in workload. But what about the qualitative and post hoc analysis? Here's where it gets interesting. There were a number of usability challenges in the different technologies, and each tech had its own unique pitfalls. In the non-AR condition, zooming too fast using a 2-finger pinch motion was a common problem. This caused people to slingshot themselves straight through the red planet and out the other side, which was quite disorienting. In all 3 conditions, people had trouble closing dialog boxes and pop-ups because the actions for navigation and interaction were only subtly different, and sometimes the buttons were hard to press. Comparing the tangible AR technology to the tabletop and non-AR, we noted that bimanual interaction presented some challenges. A few people remarked something like, "I wish I had an extra hand," because unlike the other conditions where a user could use a single hand, the tangible AR either required both hands or for the user to place the tangible on a surface, like a table or their lap. Outside of the study, after officially finishing, we invited people who made comments like this to try a phone holder stand so that they could use both hands to manipulate the tangible, and this seemed to be a popular solution. Regarding demographics, there was something else interesting that we observed. So, in the tangible AR condition, some older folks and people wearing glasses would tilt their head back while extending the tangible as far away from them as possible to see. We wondered if this was perhaps farsightedness manifesting as a need to increase the distance between eye, phone, and tangible. Interestingly, many people wearing glasses did not self-identify as having a vision difference. It may be that the familiarity of daily wearing glasses eroded their awareness of their eyesight as a vision difference. Perhaps most interesting, though, was just the excitement from expert astronomers about how they might use these technologies in their research. We had a surprising number of study participants who worked at or with planetariums and who saw these tools as a way to get the exciting, large-scale astronomy data visualizations that they were creating in the dome into the hands of people in situ, such as in the classroom or while reading a paper without a computer nearby. Lots of folks we spoke to were excited about these tools for K-12 education or outreach in their lab. For example, one teacher explained how they wanted to teach students how sundials work, but they are only in the classroom for a single hour. Having an interactive 3D simulation with day-length animations made this much easier. One person in radio astronomy analyzing all sky data noted that their data was spherical in shape, and they were especially excited by the tangible AR device because users would be able to quickly rotate their data with many degrees of freedom. In both AR conditions, there were comments about how existing data visualizations don't quite cut it for their scientific needs. One participant mentioned frustration using Matplotlib, and another said they wish they could use 3D visualization more in their research, but they had trouble using the technology. They saw these solutions as more accessible, and they were curious about how to create their own. Overall, between the quantitative and qualitative results of our study, we observe a tension. On one hand, quantitatively, non-AR technology is lower or about the same workload as the AR technologies, so there's no clear benefit to using AR when it comes to workload. But qualitatively, people were super excited. They could draw a clear line from the things they were seeing in our study and how AR could help them explain and communicate scientific information about our known universe to a wider audience. The potential benefits of AR that they described for their day-to-day scientific work were specific and notable for their visualization utility, even outside the field of astronomy. We think this tension is a promising area of research. The challenges evidenced by the workload scoring are not insurmountable. Our work has carefully cataloged a number of these challenges, and we even observed in real time what some potential solutions could be, such as using a phone stand, obeying Fitts' law for button sizes, and making distinctions between interaction and navigation actions. We think these results are useful beyond the field of astronomy. Many of these interaction types and data types are relevant to other fields as well. A preprint of this paper and supplemental data, including our full statistical analysis and anonymized quantitative and qualitative results, are available on OSF. Thank you.